Yes, and I was saying we certainly want to contribute, and we do so by assisting the steel rolling industry in preventing rejections, increasing yield, and reducing fuel consumption. Just to familiarize the panel and the audience with us, we were incorporated in 1985 by metallurgists from the internationally acclaimed Indian Institute of Technology, Mumbai. And that's why most of our work has been in the hot rolling, hot forging, and heat treatment industry. Due to the highly customized products that we develop, based on each unique process, we are sole suppliers of these specially developed coatings and lubricants to industry leaders in many countries in Asia, Europe, and USA. Process losses or problems faced by the industry are our starting point for developing products using combined knowledge of metallurgy, chemistry, and tribology. We always start with the simulation tests in our own lab, revalidate it in highly technical and well-equipped labs like BFI Germany, CCRT Thane, and a few others. The products are further pilot tested in steel mills and forging organizations that are interested in solving their problems and have the patience for development. After 2 or 3 such organizations certify, the developed products are put forth for industry implementation. These are some of our valued customers. Some of them have supported us in developing the products. The others simply pushed us hard for results, and we thank them both equally. BFI Germany is a lab that carries out applied research for the hot rolling industry. Dr. Miriam Sartor here helped us by carrying out various kinds of tests to validate the anti-scale protective coatings manufactured by us. CCRT Labs Thane, most of the panel members may be knowing them. It's headed by Dr. Sanjay, and they have helped us in validating the refractory coatings that we manufacture. I thank them. Profitability of a hot rolling mill is secured when rejections are prevented, yield is increased, and fuel is saved. And the good news is there are protective coatings that meet each of these requirements. My presentation includes case studies of each of these. When steel is heated at high temperatures, 2 phenomena are inevitable: oxidation and decarburization. Oxidation, or scaling as we call it, can be seen on this billet, heated prior to hot rolling, this ingot, heated prior to open die forging, and this billet prior to hot forging. This painful picture here shows the hot rolled material being gas cut to be scrapped. Reason: excessive decarburization and scaling that is not accepted by the stringent automotive customer. Can you imagine the loss of resources in rejecting entire heats? In any organization, rejections range from 3% to 15%. And about 50% of these rejections are directly or indirectly associated with scaling and decarburization. They also add expensive processes like peeling, acid pickling, grinding, etc. These processes add costs but do not add value to the product. Rejections due to scaling and decarburization occur when billets are excessively heated due to mill breakdown and various such reasons. Scale pits, as seen in these billets heated for forging. Oxygen reacts with metal to form metal oxide. The same oxygen that breathes life into each one of us also kills tons of steel and burns crores of rupees every day. Oxygen has a thermodynamic affinity to metal. The more the temperature and time, the higher the scaling and decarburization. Scaling and decarburization can either be prevented or substantially reduced by creating a barrier between oxygen and metal. This is done by the use of ESPON protective coatings. The coatings are non-hazardous and do not alter heat transfer. Method of application is simple. Details of return on your investment are just about to be unveiled. These are billets coated before hot rolling to control scaling and decarburization. In the hot rolling of rail steel, the part that comes in direct contact with the locomotive is of utmost importance. Here, decarburization needs to be controlled to bare minimum. If not, it could lead to rail breakage, risking lives of passengers in the train. You can see that coating is sprayed only on the side that comes in contact with the locomotive. Heated to 1270 degrees Celsius, soaked for 42 minutes. And the result, on the coated side, on the not coated side, you can see white decarb layer has penetrated deep. On the coated side, decarb is controlled well. A case study from Marmagao Steel Limited, decarb was 0.3 mm. The coating helped in bringing it down to 0.08 mm. In this case study, bar peeling was reduced from 2 mm to 1 mm as the coating consistently controlled decarburization and scaling. You can appreciate the material saving and time saving in this case. This is a case study from Vardhaman Special Steels Limited, Ludhiana, informing the various grades where they consistently control decarburization using the coating. We thank their Senior General Manager R&D, Mr. Tippanwar, for independently and successfully implementing ESPON protective coatings at both stages, as he has mentioned here. Billet heating to control decarb, reduce scale formation, and to improve the surface finish, and also before annealing to control partial or full decarb on the grades that he's mentioned here. Coating can be sprayed at ambient temperature as shown in this picture here. Very less time is required to coat the entire heat. And the result here, on the left is a not coated billet with sticky scale, as you can see. On the right is the ESPON coated billet that shows very less scale. In expensive grades of steel, it helps even if scaling is reduced by 50%. These are stainless steel ingots coated with the sole aim of reducing scale loss and increasing yield. Again, the comparison between not coated versus coated ingots after heating are visibly remarkable even before measuring the scale thickness. Coating can be sprayed at high temperatures too. This is an ingot at 630 degrees Celsius being spray coated. The same can be carried out for continuous cast hot rolling mills as well. And finally, the result of coating. On not coated ingots, 5.5 mm thick scale is formed here, as you can see. And on ESPON coated ingots, 2.5 mm thin scale is formed. The texture of scaling and its aggressiveness is also proof of reduction of scaling. Target of achieving 50% reduction in scale loss surpassed. A testimonial from Walson Lever Corporation, Taiwan, confirming that the coating helped in controlling scale in AISI 416 grade of steel. Hot forging billets heated at 1250 degrees Celsius generate scale pits, and forgings were rejected. You can see the scale pit here. There's no way that this can be machined off. It's a straight away rejection. On the right are the billets that are coated and heated. On the dropout billet, you can see the coating here as opposed to the scaling, and the surface finish is much better, free from scale pits. This is a case of hot rolling of expensive metal alloy of high hardness. And due to consistent reduction in scaling, the initial thickness could be reduced by approximately 11%. You can see a 4.5 mm thick sheet here at the start, final thickness 3.7 mm. And by the use of the protective coating, which consistently reduced the scaling, the initial thickness could actually be reduced to 4 mm. And more importantly, the grinding time was reduced by more than 50%. Again, since this is an expensive alloy, there's an approximately 11% saving in metal itself. Here is the letter of appreciation we received from Medhani for this case study. At Rourkela Steel Plant, 3 shot blasting operations were needed to remove thick adherent scale generated on steel plates. By the use of protective coating and reducing scaling, dispatch could be effected by only a single shot blasting operation. That's a 66% improvement in the shot blasting operation. Forging billets of SAE 4320H. You can see the extent of damage due to scaling after annealing. In spite of giving a shot blasting time of 20 minutes, the stains and the scaling has still remained. In contrast, the coated and annealed billets have a very good surface finish. Short blasting time is reduced from 20 minutes to only 12 minutes, 40% reduction in short blasting. This is a certificate of recognition awarded to us by Tata Innoverse for preventing a formation of scales on steel tubes. Our technical director collecting the award. Well, after preventing rejections and increasing yield, we move on to the next important cost center, furnace operation and the coating that generates substantial savings in this area. These are the benefits proven that I will substantiate with case studies. Before that, a quick look at the product. This is a new refractory lining that you'll see. The masons usually have a habit of applying some local putty that neither has high heat resistance nor good adherence. And this is the reason most of you may have noticed the amount of time and fuel taken by a furnace to achieve the temperature of 1250 degrees only increases with time. A newly relined furnace will take lesser time and fuel as compared with the same furnace, say after 6 months. The reason being thermal shocks and cracks of refractory. Another important indicator, the furnace outer shell too becomes hotter as months pass by. Here, you can see the smooth finish achieved by the use of refractory coating on the same furnace. All gaps and cracks are sealed off, thereby preventing energy leaks. S.P.Shenoy refractory coating can withstand up to 1900 degrees Celsius. It is highly resistant to thermal shocks and cracks. It has a non-wetting characteristic, which means you will not face the problem of furnace oil impurities getting deposited on burner blocks. This is indicated by a slight luster or a shine that you can see on the coated burner blocks. Coating must ideally be applied on a new refractory lining. However, we have carried out a number of applications like this one. This refractory is already quite damaged, and the same refractory after coating, here you can see, we have tried to give as smooth a finish as possible. A quick summary of the benefits. As the coating can withstand 1900 degrees, it increases emissivity of heat. The heat is reflected back into the furnace. As a result, it keeps the refractory protected. There are a whole lot of benefits here and corresponding case studies in various applications. But for now, let me concentrate on saving fuel and reducing furnace downtime. Here is a lab report from CCRT Thane confirming that conductivity of heat is reduced. If the coating and refractory is not conducting heat, it is clearly reflecting it back into the furnace, which leads to fuel savings. The reason why I show you this small sealed quench furnace is because it is much easier to observe each parameter closely. And these are observations as given to us by the popular bearing manufacturer, NRB Bearings, after using the coating. They say that the uniformity of heat throughout the furnace increased by 8 degrees. Furnace outer shell temperature is reduced by 10 degrees approximately. So with a reduction of 10 degrees in furnace outer shell temperature, what savings can you expect? Well, the answer is given by Mr. Sandeep Rege, DGM Passenger Unit and Heat Treatment, and his heat treatment team at Mahindra and Mahindra Limited, Kandivali, Mumbai. They meticulously verified the fuel consumption in their furnaces before and after using the refractory coating. A fuel saving of 7% was achieved in this case. With a fuel saving of 7%, the return on investment of the refractory coating works out to less than 1 month. At Kalyani Carpenter Special Steel, now Sarloha, located in Mundwa, Pune, the problem faced in their ingot soaking pit was very high temperature of the furnace outer shell. It shows 130 degrees Celsius, and the only problem that they faced were workmen were finding it very difficult to move about the furnace. They were not concerned about refractory lining life or fuel consumption or whatsoever. They just wanted their workmen to be more comfortable around the furnace. And we attacked the issue by using the coating on the refractory lining. And by coating the refractory lining, the shell temperature reduced by 20 degrees Celsius, as mentioned here. Fuel saving is expected to be much more than 5%, but certainly not less. And hence, it's mentioned 5% in this case. Coating is found to be intact even after 10 months. This is an ingot soaking pit at 1250 degrees run regularly. A case study from one of the TMT bar making hot rolling plants located in Vada. In their billet reheating furnace, the coating enabled substantial increase in refractory lining life from 11 months right up to 21 months. Sorry, 12 months with coating, without coating 12 months, and with coating 21 months. Fuel saving of 5% is confirmed here. This is in the case of furnace oil. And finally, my last case study, which is actually a worst case scenario. Ironically, it is also one of the best case studies that I have to present here. At Jindal Stainless Hisar Limited, they have highly efficient furnaces designed and supplied by Andritz, Germany. Very fuel efficient. The outer shell temperature is not more than 45 degrees Celsius. No problem of refractory or any other issue whatsoever. The only reason the coating was tried here was with the aim of reducing fuel consumption. I thank Mr. Sushil Jain, General Manager, and his team for closely monitoring their fuel consumption before and after coating over a period of 6 months and putting forth this data for the benefit of us all. The reason I said this is a worst case scenario is because the saving achieved here was approximately 1% only. And in spite of just a 1% saving, the return on investment is 1 month only. With these consistent results that show an ROI of 1 month or less, the use of ESPON refractory coating is undisputedly the easiest technique to achieve substantial fuel savings in furnace operations. Well, I thank you all for your time, and I'm open to questions now or offline on the given contact details. Thank you.